Hi boys and girls, welcome to your final lesson of this term for physics, and we'll be looking today at activity, count rate and half-life. So in your fact book, please have this page opened up from the physics section. By the end of the session, we will understand what radioactivity is all about and the idea you can't predict it. Its activity is the rate at which source of unstable nuclei decays, and we'll understand a bit more about this. We'll compare activity to count rate, and we'll then be able to tell us the half-life and how to work it out, and be able to either draw, sketch, or interpret from half-life graphs. Before we do that, as usual, a starter. Please pause the video, give yourself about 5 minutes to answer these questions as best as you can. Answers are coming up in a little while. Okay, so here are the answers you should have got. Describe the structure of an alpha particle, a beta particle, and a gamma wave. Well, alpha is positively charged, 2 protons and 2 neutrons, a bit like a helium nucleus. Beta, fast-moving, negative charged electron. My mistake, I've misspelt it there, but it should say electron. And gamma is an electromagnetic wave. It has no charge and no mass. For part 2, it said describe the structure of an atom. Well, an atom has a central nucleus, which is made up of positive protons, neutral neutrons. Around this nucleus, there are negative electrons orbiting around in shells. Number 3, how many times smaller is the nucleus compared to the atom? Well, it's 10,000 times smaller. What's between the nucleus and the electrons in the outer shell? Empty space. Number 4, explain what happens to the mass number of an atom which decays by releasing alpha particle. Well, an alpha particle is 2 protons and 2 neutrons, so an alpha particle has a mass of 4. If the nucleus loses the alpha particle, its mass number must lose 4. It decreases by 4. And last question, explain which ionizing radiation is most harmful inside the body. Well, again, the answer is alpha. And the simple reason is because alpha can't penetrate through the skin, it can't penetrate through the layers of the organs. So what happens is it gets absorbed by the organs inside your body. We also know alpha is most ionizing, therefore it will cause most damage to the DNA, which could lead to mutations and cancer and cell death. So inside the body, alpha is most harmful. Okay, so let's make a start to the lesson. What is activity? Before we answer that, I'd just like to remind you that unstable nuclei release radiation to become more stable. And this happens randomly. We don't know which of the nuclei inside a radioactive source, that could be a lump of radioactive rock, for example, we don't know which of the atomic nuclei will decay. It's a random process. But we do know that it continues to happen until all of the nuclei have decayed. So the process of radioactivity is random and continuous. So activity, well, its definition is that activity is the rate at which radioactive source decays. Rate just means how many decays per second. So I'll give you an example. Activity is measured in the unit becquerel, which is capital B small q. So 1 becquerel means one nucleus decays per second on average. Activity is measured using a Geiger-Müller tube. Now I would like to know that activity is talking about the rate, so it's pretty much on average. It doesn't happen all the time. It doesn't mean that each second you will guaranteed get. So on average, you'll get 1 decay per second. Count rate, on the other hand, is the number of radioactive decays that are detected by a detecting machine like a Geiger-Müller tube. So the count rate is to do with the actual detecting machine. It counts how many ionizing events happen. So count rate is measured in the unit per second. So you might have, say, 3 counts per second. That means that there are 3 ionizing radiations going through the counter each second. The problem with count rate, however, is it can be affected by background radiation. So the count rate doesn't necessarily mean that the radioactive ionizing radiation is coming from a source, particular source that you're aiming it at. It could be also affected by the background radiation. And if you remember from last lesson, background radiation is radiation, low level, that's always around us. Please pause the video right now and copy down these definitions of activity and count rate. Okay, so let's move on to half-life. Now this definition of half-life is very important. Half-life of a radioactive source is the time it takes for half of the nuclei to decay. So a radioactive source is made up of radioactive nuclei, unstable nuclei. Half-life just means the time it takes for half of those unstable nuclei to release radiation and decay. So you'll notice from the graph, the shape of it is always a negative exponential shape. So it's a curve that goes downwards. This is very important because in an exam, they might ask you to sketch it. Sketch means you don't need to put the numbers down, just the general shape. So it's important to know a half-life graph always follows this curved downwards shape. You'll also notice that on the y-axis, the axis going upwards, is always to do with radioactivity. So it could be the count rate, it could be the number of unstable nuclei, it could be anything related to radiation. The x-axis, the axis going along, is always a measure of time without fail. So it could be days, as the example on this graph, or it could be minutes, or it could be years, or it could be millions of years. The x-axis is always a measure of time. And it's very easy and important to know how to work out the half-life of something using this graph. Before we go any further, please copy this information down. So, I'm going to show you how to work out the half-life using this graph. You'll notice that the radiation x-axis count rate starts at just a little bit above 1,600. Half-life is really simple to work out using a graph. Step 1. Work out half of the starting count rate, or the starting value on the y-axis. So it's just above 1,600. So in this case, half of just above 1,600 is a very small amount above 800. Then you draw a horizontal line across from your halfway point to just where it touches the graph. Now I'd like to highlight here that the halfway point on the y-axis isn't the halfway point of whatever the y-axis goes up to. So in this case, it's not the halfway point of 1,800. It's the halfway point of where the graph, the curve, starts on the y-axis. So here, if the graph or the curve started at 1,000, the halfway point you'd count at 500. But in this scenario, let's go back to 1,600. Halfway point is 800. You draw a line across until it touches the graph. Then you draw a line downwards. And wherever it lands on the y-axis, that value, that number, is your half-life. So in this case, it tells us that it takes, on average, 20 days for the count rate to half from 1,600 to 800. Can we do this again on the same graph? Of course we can. So if we now take 800 as a starting point, half of 800 is 400. Draw a line across until it touches the graph, go down, and you'll notice now the half-life is at 40 days. Please bear in mind that we're now taking the difference from the first half-life to the second half-life. So we start at 20 days, go to 40 days, and what do you notice? It's another 20 days. Half-life never changes for a known substance. So in this case, or for any substance, sorry. In this case, if the first half-life is 20 days, the second half-life will also be 20 days, the third half-life will also be 20 days. I'd like you to, on your graph, add this information about how to work out the half-life using a graph. Okay. The link for this video that I'd like you to watch now is just below this video. It's in the detail section. Please click on that link and watch the free science lesson video, which shows a little bit more animation about how half-life is calculated and what it means, and add any information you get from that to your notes, please. Once you've done that, come back to this video. Okay, your turn. I'd like you to have a go at calculating the half-life for these 4 graphs. Take your time, use a pencil, use a ruler. In an exam, if you don't use a ruler, you won't get the marks because it could be wrong, and every tiny square counts. We'll go through the answers in just a second. Okay, so for graph A, the curve starts at 300, so we go down to half of 300, which is 150, go across till it touches the graph, and then go down. So our half-life in this scenario is 14 days. For B, the graph starts at 10,000, half of 10,000 is 5,000. You go across from 5,000 till it touches the graph, go down, and we'll realize that the half-life in this case is about 420 years. For C, the graph starts at 100, so half of 100 is 50. Go across and down, which tells us the half-life is 6 hours. That's a very short half-life. This means that C decays very rapidly. And D, our last one, we're talking about mass now, so 6 goes down to 3. The time, half-life, is 28 years. If you've made any mistakes, please correct them. If you've got all 4 right, fantastic. But please do make sure that you've got the right answers down before we carry on. So let's talk through this one now. This is for higher physics. Sometimes you get these kind of questions. A radioactive source has a half-life of 5,730 years. A sample gives a count rate of 20 decays per second, 20 becquerel. 20 decays per second, sorry, it's a count rate. The tree died 17,190 years ago. Determine the count rate when the tree died. So, what you always do is, step 1, find out how many half-lives have passed. In this case, we know the tree died 17,190 years ago. The half-life is 5,730 years. How many times do they divide? Well, the answer is 3, so it's 3 half-lives. Step 2. We know that every half-life, the count rate halves. So we then go backwards. We double it every time. So in this case, we start with a count rate of 20, and we need to go up 3 times. So 20 goes to 40, which goes to 80, which goes to 160. So that tells us that after 3 half-lives, the original count rate must have been 160. I'd like you to have a go at these questions yourselves. They talk about how to work out half-life calculations. Please try your best, take your time doing these, use a calculator, where necessary use a pencil and ruler. Answers coming up in a second. We'll go through these first. Okay, this is where you should go answer-wise. Please bear in mind to correct any mistakes that you have. If you have any questions about these, please drop me a question in the chat box in the Teams chat. I'll be happy to help you out, or drop me an email. Finally, we've talked about what radioactive decay is, activity, count rate, half-life, and I'd like you to finish by having a go at these questions. Answers are